Hi, so I'm Hadas Benisty. I'm working today during my postdoc today with Ronen Talmon, and this work is our previous work from my PhD with Professor David Malach and Professor Kobe Kramer. So today we're going to talk about voice conversion. I'll explain what it is, what's the motivation, some general schemes, and we'll discuss a common method for voice conversion, which is based on GMM modeling. And I'll present our proposed approach, which is called a grid-based voice conversion method. We'll talk a bit about its formulation. There are going to be a little bit of Greek letters, but not too much. We'll talk about some experimental results that we have and conclude. So the general setup for voice conversion, we have a sentence said by a source speaker, and then we want to apply some conversion function and make it sound as if it was uttered by a target speaker. So in order to obtain this conversion function, obviously we need some voice samples of the two speakers. So generally we have a data set of the two speakers. So the application for such thing, for example, personalization of text-to-speech. For example, IBM has a text-to-speech system which is trained and based on recording of professional narrators, recording thousands of sentences. So obviously, they cannot record the text-to-speech system to speak in any voice you would like. So if you would like to personalize this system, we could apply a voice conversion system outside the text-to-speech and make it sound as if someone else said it. Also for any dialogue systems, people with vocal pathologies, and for entertainment and toys, probably the money lays there. So what are the speech characteristics? So we as humans, how do we perceive the speaker's identity? So in most cases, we respond to the prosody attributes, which are the pitch. For example, females and women and children have very high pitch values, and mostly men have lower pitch values. And also the rate of speaking. For example, I talk rather fast and someone else will talk rather slow, so we will respond to this. And also the energy, if someone is very loudly speaking or very, we all heard it in Seinfeld. And also the spectral envelope, if a person, the structure of the vocal cords, the way a person moves his lips, his tongue, his nasals, affects the sound. So even though the prosody attributes are more important, the pitch is usually modified using a simple linear conversion function using the mean and standard deviation. And most voice conversion methods concentrate on converting the spectral envelope. So we will also deal with the spectral envelope. So the training data, in most cases, we would assume that we have sentences said by the two speakers where they say the same text. Meaning we have, say, a couple of dozens of sentences of the source speaker reading out several sentences, and also a couple of sentences of the other speaker reading the same sentences. Some systems deal with non-parallel data sets, which is a much harder problem, because then we need to decide which phoneme, which utterance matches the other utterance at the other speaker. And the hardest case would be the cross-lingual data set, where we have the source speaker speaks in Spanish and the target speaker speaking in French, for example. So the GMM-based conversion, which was proposed in '98, a long time ago, is the common benchmark for voice conversion systems. It is based on a parallel data set where we align the two data sets, meaning that even if we would tell the speakers to speak at the same rate, will never get the same amount of features. So we need to align them, meaning that we'll have an MFCC vector of the source speaker labeled as xk, and then we would take, we need to know exactly on which MFCC vector of the target it matches. So once we have this parallel and aligned source and target training vectors, the MFCCs, we train a GMM model, and then the conversion function is a linear function based on Bayesian estimation. So the GMM conversion method, it has several drawbacks. First, its training is exhaustive, as you know, it's iterative, and since we don't have much data, it's often leading to ill conditioning, even if we train diagonal covariance matrices. Also, since the conversion itself is linear, it's often oversmooths the spectral envelope, which leads to muffled synthesized speech, and we will hear it. I hope you can hear it here in the system here. Okay, so our proposed method is called grid-based conversion. We look at the voice conversion task as a Bayesian tracking of the target spectrum, where the observed data is the source spectrum. So at the conversion process, we evaluate the converted spectrum as a weighted sum of the target training set, meaning the MFCC vectors we have at the recorded session, and use them as grid points. Hence the name grid-based. So this is like the exhausting couple of slides, but bear with me. So we mark the target spectrum as YT, and we assume that the spectrum of the target at time t is somewhat Markovian, and it depends on the spectrum at the time frame before through some function f and a noise u. Also, since the source and target speakers say the same text during training and also during testing, since we want the converted sentence to be the same text but in another voice, we assume that the source spectrum is connected to the target spectrum through some function h of t and a noise. So the optimal Bayesian estimation would be to take the expectation value of yt, of the spectrum of the target, given the time frames of the source. So practically, we obviously do not have this function, this posterior function. So we use a grid-based approximation for this function. So our discrete approximation is given parallel but unaligned training sets, meaning that we do use a parallel training set where the two speakers say the same text, but we do not need to have a one-to-one match between these feature vectors. And then we evaluate the posterior probability as a discrete sum, meaning that we do not know what is P for any MFCC vector of the target, but just at the points where the MFCC of the target equals to MFCC vectors we saw during training. So the optimal estimation becomes a weighted sum of the training points of the training data of the target. So our sequential estimation is of two stages. At the first stage, we do prediction. This is very similar to filtering. We start with a prediction where we use the red probability, which means what is the probability of having some MFCC of the target, given we had another MFCC at the previous time frame. And the next stage is to update. And here we use the likelihood probability, meaning what is the probability of having a certain MFCC vector of the source, given we saw another MFCC of the target. And obviously, we need to give the algorithm these two probabilities, the evidence probability and the likelihood probability. So this we use, here we propose some modeling for these probabilities. In natural speaking, sequential MFCCs would be similar but not identical. Therefore, we use this exponent function where we say that inside a radius of y, we give the same probability for two MFCCs to be subsequent. But if they are too far, this probability deteriorates, diminishes. Also, the likelihood modeling, we need to give some value for the probability of having a certain MFCC at the source given some MFCC of the target. So this is quite problematic since we have a limited training set of the two speakers. So we cannot predict given any MFCC of the source. That's why we're using an interpolation function, an RBF interpolation, of the discrete likelihood, where we give, we need to model what is the probability of having some xm from the training set given some yk from the training set. This is the last slide with the formulas. And so the discrete likelihood, we are using the fact that our data set is parallel. So if a feature vector from the source and a feature vector from the target relate to the same phonetic sequence, then we say this probability is not zero, and otherwise it would be zero. So to summarize the algorithm, we are giving a sequence of feature vectors from the source speaker, and we initialize them. And then we iterate. We evaluate the prior weights, the posterior weights, and obtain the converted spectra as a weighted sum of the training set. So in order to examine our method, we compared several methods. We compared our proposed grid-based approach and the GMM method. And obviously, since the GMM method leads to muffled synthesized speech, we also used some global variance enhancement methods in order to inflate the spectral features. So this can be done in two ways. We used our own integrated global variance enhancement, which is called CGMM, presented a couple of years ago, and also our post-processing block, which we presented a year after. So these examined methods are the GMM with our global variance enhancement block, the proposed grid-based conversion with the enhancement, and the incorporated CGMM. Just to look at the temporal evolution of these methods, the upper graph is the first component of the MFCC, and the bottom graph is the third. You can see that the green line is actually has a lower global variance, where this is the GMM, where the red line, which is grid-based, it's much less. It has a greater variance. So objectively, how do you say that a conversion works? You measure the spectral distance between the converted spectrum and the target spectrum. And since you get a number like 6 dB, you don't know how to compare them. We normalize them with the original distance between the source and the target. So obviously, a normalized distance of 0 would be good. Also, the global variance is important in order to not to get a muffled sound. So we measure the normalized global variance, where a good number would be 1, meaning that the global variance of the converted spectra equals the global variance of the target spectra. Okay, so to shorten up, you can see that in most cases, the grid-based conversions leads to the highest normalized global variance and to the lowest ND. And subjectively, we did some listening tests. And you can see that our proposed approach leads to the best results, meaning that the converted spectrum, the converted signals were marked as most similar to the target spectrum. And this does not come without a price. The quality, obviously, is less good than the CGMM. So just so you can impress, this is for converting a male speaker to a female speaker. So this is the source.
He was manifestly distressed by my coming.
And this is the target.
He was manifestly distressed by my coming.
And these are the three methods we compared, the GMM.
He was manifestly distressed by my coming.
The CGMM.
He was manifestly distressed by my coming. He was manifestly distressed by my coming.
So obviously they all sound the same to you because you don't have headphones, but you can have some sort of feeling of how the voice conversion hears. And another example.
Then came my boy code.
Then came my boy code.
Then came my boy code.
So you can see that since we do not convert the prosody, it sounds like the other speaker imitating the previous speaker. So to conclude, also I didn't mention that these results are using 10 sentences only. Okay, since we assume having a parallel data set, it would not be, no user would agree to record himself saying like hundreds of sentences. So having 10 sentences is sufficient using our method. And subjectively, our method is most similar to the target speaker, but with lesser quality. So thank you.
Do you have the results of your conversion judged by human listeners? And how do the judgments correlate with your numerical evaluation?
So what we've presented is the subjective listening test, because I didn't have time, so I went very briefly. The people said that our method leads to more similar to the target. It is more similar to the target, but with lesser quality than the other method.